Welcome to another video for organic chemistry. In this video, I'll be discussing rearrangement reactions of carbocations. For our first reaction, we're going to deal with a 3-methyl-1-butene. If you recall from your naming system, that 3-methyl is referring to the third carbon and the methyl group that's attached to it. And then our 1-butene is referring to the double bond attached to that first carbon. So we're going to take 3-methyl-butene and create a reaction with hydrochloric acid. So we're going to discuss the mechanism of how the chlorine and hydrogen, how and why they end up where they do in this reaction. So the hydrogen will first take the electrons from that double bond. It will take those electrons, and when it does, it creates a methyl group at the end and a positive charge in our second carbon. Okay? Now, from here, you can predict where the chlorine will attach, and it will attach to that positive carbon. Okay, so from that second degree carbocation, you will create a minor product. Now, there's actually another version of this molecule that is more preferable, that is more likely to happen. Now, why? So we'll go back to our previous image. So here you see again, we have our second degree carbocation. Now, if you recall second degree carbocations and how they compare to a third degree carbocation, third degree carbocations are more stable. So thermodynamically speaking, this molecule would rather be in a third carbocation state, rearrangement. So what you're going to notice here is you're going to see that the hydrogen on our third carbon, it's going to take its electrons and it's going to shift over to the second carbon. That's what you call a hydride shift. So the hydrogen and its electrons will move over, and that positive charge will then shift over to the third carbon. Okay, so our hydrogen with 2 electrons shifted, creating a CH2, and then our positive charge shifts over to our third carbon, and you notice that that carbon is attached to 3 other carbons, creating a 3-degree carbocation, which is much more stable than our second-degree carbocation that we had previously. So in this reaction, you're going to end up with a hydride shift because thermodynamically it would much rather be in third-degree carbocation state than second-degree. And this was going to be the location of our halogen bond. This is where our electrophile will meet our nucleophile, chlorine, and we create a bond there. So those 2 electrons from that chlorine will create a bond with carbon. And this will be our major product. This is the most stable form of this molecule. So our minor product does form, but at a very minimal amount. Our major product is the one that you will most likely see in this reaction due to the hydride shift, creating a third-degree carbocation. All right, let's move over to our second and final idea, our methyl shift. So we have a 3,3-dimethyl-1-butene. So again, notice the 3 carbon has 2 methyl groups, dimethyl, and then our first carbon has that double bond. Okay, so again, hydrochloric acid will come into the picture. The hydrogen will take that double bond, and you're going to see that CH2 group at the end turn into a CH3, a methyl group, and that will create a positive charge on our second carbon, creating a 2-degree carbocation. Now pay attention to our methyl group at the bottom. Now it could happen with either one, the top or the bottom. It's going to shift. It's going to shift over to that second carbon. That's what we call the methyl shift. That's a methyl group shifting over. And that positive charge now moves over to the third carbon, creating a 3-degree carbocation, a more stable version of itself. Now here, like our previous one, so our carbon being the electrophile and needs electrons, it loves electrons, and our nucleophilic chlorine, which wants a nucleus. So those electrons, it wants to share those electrons, and carbon needs electrons to be shared. So this will be the location for our bond, our chlorine. So in summary, we talked about hydride and methyl shifts. These shifts are driven by thermodynamics to create more stable molecules. So if you have a second degree, and if it has the option and the space to create a third degree carbocation, then it will. Okay, because again, these are driven by thermodynamics, but they're limited by the amount of space they have, the amount of extra room they can create. These products are predictable based off of paying close attention to the number of carbons you have and where the positive charge can be shifted in those molecules. Okay, well that summarizes and that does it for rearrangement reactions of carbocations. I hope this was helpful. Thanks for listening and good luck in your study.